हेलो दोस्तों, स्वागत है आपको हमारे चैनल में, जहां हम पढ़ने वाले हैं फिजिक्स के कुछ तड़ाकेदार कॉन्सेप्ट्स। आज हम पढ़ेंगे, कंटिन्यू करेंगे इलेक्ट्रोस्टैटिक्स का वही कॉन्सेप्ट जो हमने अधूरा छोड़ा था। उस कॉन्सेप्ट को हमने पूरा कर लिया था। उसके बाद जो आएगा कॉन्सेप्ट, उसी पे हम फोकस करते हैं। तो इससे पहले वीडियो में हमने क्या सीखा था? इलेक्ट्रिक फील्ड ड्यू टू ए पॉइंट चार्ज। Electric field due to a point charge. Now, what are we going to study, or what are we going to learn, that if there is a system of point charges, there is a system of point charges, like this is a coordinate system. Something you will be recalling, we did something similar in previous classes where we learned how to find the collective force of a system of charges on a charge, on a given point charge. Here it is also similar. You have been given a system of charges like this, like this, like this. All are discrete in nature, that is, we can exactly locate the point of that charge. Okay, so for this system, we need to locate the electric field at this point. We need to locate the electric field at this point for such a system. So what are we going to do? Like, you just name them like Q1, Q2, Q3, Q4, something like that. Q1, Q2, Q3, Q4, and like there are a lot of charges, let it be Qn. Then just look at that vector from there. Something like that, many position vectors with respect to those charges. So for Q1, we find that it is R1. For Q1, it is R1. So for Q1, let the electric field at this point P be E1. Okay? It is a vector quantity. Just put a vector above it. Then for Q2, it's E2. For Q3, it is E3, and so on for Q, and for the nth charge, you get En at this point P. Okay, and before this class, we just learn how to calculate electric field for a point charge at a given distance. Okay, what was that? It was E equal to 1 upon 4 by epsilon naught multiplied that given charge divided by r square. What is r? R is the distance at which we are going to calculate that electric field. So, what will be the net electric field at this point? What will be it? Let that electric field be E. So, what will be it? E1 plus E2 plus E3, and it goes on. It is a vector sum. Mind it, it is a vector sum. You add them in the vector method, not algebraically like 1 plus 2 gives you 3. But this is not in this case. You have to add them simply in vector addition method. So, what is the formula to find the net electric field at point P? You need to calculate all individual electric field and then add them vectorially. Add them in vector addition. Use vector addition method to find the last result. So this is called superposition of electric field at point P. This is called superposition of electric field at point P. Superposition. So what does this superposition tells you? Electric field. It tells you that to find the resultant electric field at a point P due to a large number of point charges, you can say large number of point charges, or you can say a given number of point charges, you will find the electric field due to each individual point charge at point P and then add them in vector addition method, and this is what it is, superposition of electric field. So I just conclude that you have understood this concept. So let us jump to the next concept. See you in a while. Oh, I just forgot to write that principle. So what does the superposition of electric field principle says? It states that it says that the electric field due to a group of point charges is equal to, it says that the electric field at a point, sorry, I have to include it, at a point due to a group of point charges is equal to the vector sum, is equal to the vector sum of each individual charge, vector sum of electric field, sorry, of electric field of each individual charge at that point. Okay, this is what the principle states. What does it say? Says that the electric field at that point due to a group of point charges is equal to the vector sum of the electric field of each individual charges at that point. And the other thing, that condition is, we assume that other charges are absent. So what does this means? When we try to calculate the electric field of Q1 at point P, we are going to consider this, the charges are absent. The charges are absent. Likewise, when we try to calculate the electric field of Q2 at point P, we consider that the other charges are absent. So we try to find out their individual electric fields and then add them in vector addition method. So let us jump to the next concept. Now we shall be learning about electric field due to some continuous charge distribution. So first of all, we need to learn or we need to know, हमको क्या पता होना चाहिए कि continuous charge distribution किसे कहते हैं और इसकी जरूरत हमें क्यों पड़ी. So let us understand first of all continuous charge distribution. Continuous charge distribution. As we know, charge obeys quantum nature. As we know, charge obeys quantum nature, or it is discrete. We can just find given from the formula. We know that Q equals to N E. What is E? It is a charge on an electron. N is a number. N is only a number. You just add those electrons at a place and find the charge that it is getting bigger and bigger and bigger by multiples of the smallest charge we have in this possible atmosphere, that is electronic charge 1.6 into 10 raised to the power minus 19 coulomb. And if we are going to consider its sign, it is negative. Okay, so but in our daily lives we don't see such quantum nature of charge. In our daily life we don't see it. Actually, we don't see an electron coming out of this point and we are going to calculate the electric field of that electron or this charge at this point. We do not see such situation in our daily lives. What we see in daily lives, like this is a wire. Okay, this is a wire. Now let me build it continuous. So a current is flowing through it. A current is flowing through it, and what do we know? Current, it is the flow of charges. It is the flow of charges. So charges are flowing from here and to this point. Can we calculate charge on this point? On this point, actually on this point, can we calculate it? No, we cannot calculate it because it is not certain that we are going to find the value of exact magnitudes of that charge. We cannot find that. So we define some other terms. So we will come to that point later. So first of all, understand, we need to find the force on a point charge Q naught. We need to find force on a point charge Q naught due to a continuous charge distribution. We need to find force. Continuous charge distribution force due to continuous charge distribution on a point charge. Okay. So now let us consider any object. It is charged. Let this object be like this. Consider it three-dimensionally. Let this object be like this, and Q naught is here. Let distance of this point from this charge is r. It is r. So we need to find with what force this object, it is a charged object, exerts on Q naught. What is the amount of force? So let it has a large amount of charge. Like at this point, let that charge be dq. Let that charge be dq. dq means a small amount of charge. A small amount of charge. So for this dq, we consider that the force acting on that Q naught is df. Okay, so df is the amount of force acting on charge Q naught, point charge Q naught due to a small, it is a large charge, but we are considering only a small part of it, a small fraction of it, that is dq. So what should be df? It should be like, you just include all those constants which we used while calculating electric field at points, multiplied. You multiplied Q naught into dq, that is the amount of charge. For you not to getting confused, we just place a bracket there, divided by r square. And you know that what is the direction of that electric field along r. Or sorry, the direction of force, that is r cap. So this was all about a small charge exerting a force on Q naught. So we need to find the whole force due to this whole charge. Since derivative is involved, we need to involve integration to find the whole amount of force. Like when you integrate it, df, you integrate left side, then you integrate right side, 1 upon 4 pi epsilon naught Q naught dq upon r square r cap. Okay. Now it will give you f. You just take out those constant terms. This is a constant term and Q naught is also a constant here. Q naught by 4 pi epsilon naught dq r cap by r square. When we integrate this thing under given conditions, we'll find the actual amount of force this charged object exert on that point charge q naught. Okay, so this is the force due to that continuous charge distribution, and this integration comes due to that continuous charge distribution. If it would have been discrete, then this term would be eliminated and would be replaced, not eliminated, would be replaced by a summation term, like this when we did it before, like we calculated the electric field from the superposition principle. For discrete distribution we use summation, and whereas in case of continuous distribution we use this integral. And for every case of continuous distribution we are going to use this integral. Okay, तो हम इस इंटीग्रल को यूज करेंगे. तो फिर चलिए कुछ केसेस पढ़ते हैं इसके ऊपर. ओके, सो लेट्स जस्ट स्टार्ट. So from now, as we have studied about continuous charge distribution, why do we need it? Due to that in our general world, in our daily life problems, we do not see those quantum nature of charge coming into act. All we see is a continuous distribution. So let us study the types of such distribution. It is a small concept. Like first of all, volume charge distribution. You have been given a volume, an object, a three-dimensional object, and you know its volume. An amount of charge is given on that volume, and this charge is distributed over that volume uniformly. So let us check this. This is a given three-dimensional object. It is a 3D object. It is a 3D object. A given charge is given on it. It is a large charge. So let it be Q. Okay. It is distributed uniformly over it. Q amount of charge is distributed uniformly on it. Since it is a uniform distribution, let us consider that for this small amount of volume, the charge it contains should be proportional, or the total volume, the charge on the total volume and that volume should be proportional to that ratio by the charge content in this volume divided by the volume of this small part. So we can say that it is uniformly distributed, and we can use a new term, that is volume charge density. Volume charge density. Volume charge density. What is density? Previously you have learned about density. What was it? It is mass per unit volume. So in this case we are not going to consider mass, as we are considering electrostatics. So we shall be considering that charge density. So but above all we need to first of all clarify is it volume or something else. Since it is distributed over a volume, we have termed it volume charge density, and it is denoted by rho. So what is rho? The total charge by volume. Let V be the volume of that object. So for this small part, let it contains charge dq. And for this small part, the volume is V. Then what should be rho? as we have considered the statement that it is equal to dq over dv. It should be equal to this. So rho can be this and can be this very often. So from this point, what is dq? It is rho times dv. It is rho times dv. So if we consider a volume containing charge, and from this point we are going to find electric field or electric force on q naught. Electric field or electric force on q naught, then let this distance be r. Then what should be the formula? As we know from continuous charge distribution, F is equals to q naught by 4 pi epsilon naught integration over dq by r squared r cap. dq by r square r cap. So what should be the dq? From this point we have derived the value of dq. So we'll write q naught by 4 pi epsilon naught integration over what is the value of dq? Rho dv by r squared r cap. Rho is a constant quantity. Rho is a constant quantity. Density is a constant quantity. You can always bring it out from that integral. It's your choice. Even if it is inside that integral, it is not going to affect the integral. And for just writing purpose, just take it out. Q naught rho 4 pi epsilon naught integration over dv r cap and divided by r square. Value of electric force. This is the value of electric force at this over exerted on this point charge. It is the value of electric force. So we got what? We got volume charge density. What do we got? Volume charge density. If you have not understood the volume charge density, then we can consider a uniformly charged sphere. Sphere. Let Q be the amount of charge present on the sphere and V be its volume. Let that radius be R. So rho equals to what? Q upon V. Q, we know that the volume of spherical object is 4 upon 3 pi r cubed. You can actually find that for an example. So from volume charge density or from a volume charge distribution, we find the force like this. This is the required formula. This is required formula. This is the formula. So this is the formula. It is volume charge distribution due to volume charge distribution. So we found out the force on a point charge Q naught due to a volume charge distribution, and if we find F, then we can easily find E. We just divide F by Q naught. So Q naught will get cancelled, and what will you get? E equal to rho by 4 pi epsilon naught integration over dv upon r square into r capped. So this is the value of force, and it was all due to volume charge distribution. Now let us jump into surface charge distribution in the next part. So let's start surface charge distribution. So what is a surface? It is a two-dimensional thing. A surface is a two-dimensional thing. Like everything in this world is a three-dimensional thing. Okay, there is no such thing that is one-dimensional or two-dimensional. Even if this paper, even if you consider a paper like this, when if you consider a paper like this, there is its length, its width, but it has no height, or we are ignoring its height. We are ignoring its height, but it cannot be ignored. It has a value. It has some value for micron, 10 raised to the power minus 6 scale. So there is no such thing that is surface or line. We are just going to consider, we are going to assume this, as we are physicists. We have to consider some situations like this page, like this page. It is a surface, like this page. If it is a surface, we have been given a given amount of charge on this page, so it gets distributed uniformly. Like this. We cannot actually calculate a given charge at a point. Like if we are given this point, can you find the amount of electric charge at this point? No, we cannot find it. So let us consider a surface charge. You can draw it arbitrarily, whatever. So let plus, these are the things, these are not discrete things, okay, they are very close, I have just drawn them just far apart, but they are very close. You cannot distinguish between them on this surface. So it is a continuous charge distribution. Plus, you can always use plus, you can always use minus, whatever, it is your choice. Okay, let that point be at this point. So from this point, let this, it is area vector at this point, and this point is r. Okay, what is area vector? The vector that is perpendicular at that point to the surface. The vector that is perpendicular to the surface at that point. कोई भी वेक्टर जो उस सरफेस के उस पॉइंट पे, जिस पॉइंट पे हम कंसीडर कर रहे हैं, उसके परपेंडिकुलर है, उसी को हम बोलेंगे उस सरफेस का एरिया वेक्टर एट दैट पॉइंट. So we don't need this in this situation exactly, but just for learning purpose, for knowledge. So what should be it? So in this case also we are going to find out the charge density. But in this case we see that there is no volume. We have totally ignored the third coordinate. We have totally ignored it. Okay. So in this case we have two coordinates or two axes, that is x and y. We are going to forget about z. So in this case you can say surface charge distribution, or you can say area charge distribution. So we say surface charge density. Such nice names, बहुत ही अच्छा नाम है. और इसको डिनोट करते हैं हम सिग्मा से. सो हमने पहले भी देखा था कि रो, in case of 3 dimension, we considered rho as dq upon dv, whereas dq is the infinitesimal charge and dv is that infinitesimal volume, the smallest thing we can only imagine. No such things exist, but we are going to imagine that it is very small, something that goes beyond your imagination. So surface charge density is rho, whereas rho can be written like this: dq by ds. Infinitesimal area. What is this? This is infinitesimal area. In that case we consider infinitesimal volume, and in this case we consider it infinitesimal area. So from this, what is dq? From this, dq is rho ds. Is that rho ds? S is the total surface area. And ds is that infinitesimal area, like this in this case, that it the value is ds, like in this case the value is ds, and charge on it is dq. very small charges, very small areas. So we are going to calculate force on that point charge Q naught due to this small element. Due to this small element. So what would be the force? As we know earlier from the concept of continuous distribution of charges, we know that F, or the total force on that, would be 1 by 4 pi epsilon naught divided by dq upon r squared. Okay, this should be the formula. As we know, okay, we are missing something. Q naught. You can actually cut it out from that integral. So just place dq, the value of dq, q naught by 4 pi epsilon naught integration over dq. What is that? Sigma ds. Sigma ds upon r squared. This is the value of force. The required formula. The required formula. You can actually take it out and put it back here. Let me draw it something better. It is not looking like a sigma first of all. So this is sigma. Oh, okay. So you get electric force, and for electric field you need to eliminate this thing. You need to divide F by Q naught, and when you divide the LHS by Q naught, you need to divide it on the RHS as well. When you divide it, Q naught get cancelled. What you will get, or what will you obtain? आपको क्या मिलेगा? 1 by 4 pi epsilon naught integral sigma ds by r square r cap. So whenever you find force, you can actually calculate electric field very easily. So just one charge distribution remains. Uh, Let us get into it. At that point, we shall be ignoring two coordinates. We shall be ignoring two coordinates. Like we shall be ignoring x and y and consider z, or y consider x, or we shall be considering x or z and consider only y. So we are going to be considering only one coordinate and ignore the others. Like this is my hair or a wire. Its one coordinate is long enough, like a wire that is 10 kilometers long, or like 1 kilometer long. So we say that it has only length, and we ignore its thickness and other things. So we consider that as a three-dimensional one-dimensional object apart from that three-dimensional object, or a two-dimensional object. Its length or its one coordinate is very greater than the other coordinates, so much greater that we can ignore those two coordinates. Okay, so this is surface charge distribution. Now let us come to line charge distribution. And from the simple distribution, charge distribution, we are left with the line charge distribution or linear charge distribution, whatever you can say. So just consider a line, given line, extending up to infinity from there, infinity from there. So a given amount of charge, or you can just not say it infinity, it is a line of some considerable length. So just and just assume a point, an element like this. Okay, an element like this, it is a straight element, not curved. We are going to consider such small things that it is a straight thing. You should not be worried about this straight or curved like this. Let the distance be dl, and it is q naught. This distance is r. Let charge on it be dq. So for all these purposes, we consider another term known as lambda. What is lambda? It is linear charge density or linear charge density. So what should be lambda? dq upon dl. And what is lambda? Linear charge density. charge per unit length. What is the amount of charge per unit length of this given length? So, and from this we get dq is equal to lambda dl, which we shall be requiring after this. So we know from the direct formula that F equals to 1 upon 4 pi epsilon naught q naught into dq by r squared r cap. Let's just take out those constant terms like q naught by 4 pi epsilon naught dq by r square r kept. Write it along. 4 pi epsilon naught, we are at the last point, like dq is equal to lambda dl by r square r kept. It is a force. It is your force on that charge q naught. And to find electric field, just terminate q naught and replace F by E. So from all of this, what have we learned? We have learned that for a discrete charge distribution, we need to calculate electric field of each charge individually and then add them vectorially. And for continuous charge distributions, we need to conduct the problem like this. The problem should be given, so lambda, the distance should be given there, and we know all of this. So this is it. We have learned about distribution, continuous charge distribution. There are types, and let us now jump to the next concept.